Okay, now I hope you are able to see this screen here. And for this particular problem, we would like to apply slope deflection equation method to solve for the P critical. And for these two examples, we can easily get the P critical by knowing what is the effective length and using the Euler equations, then you can get the P critical. So we are going to use slope deflection equations to compare and to confirm that the same critical load will be obtained for these two cases, example 2A and example 2B. Now, this is an example where what we call there is relative translation of one end relative to the others. So if I draw a particular line here, or if I draw a line here, then this, if I call this as NA and this is NB, or this is also NA and this is NB, then there is a relative translation of delta of NB relative to A. The same thing here, we have relative translations. And we have our axis here, X, and this is Y. Same thing, there will be X here, and this is Y. Okay. So now we will look at how we apply slope deflection equations where it involves relative n translation first and without n rotations. In this case, the n rotations here, which is theta A, and also here, which is theta B, they are both equal to 0. This is also equal to 0. So we will look at first case that there is only n translation and how we make use of slope deflection equations to solve for the P critical and what are the steps involved and what is the difference when compared with the case where there is no n translation delta. Then we will go to the case where both n translations, which is theta A here, and it is not equal to 0. So there is n translation at A, n rotations, but there is no n rotation at B, but there is n rotation at A. So n, there is n translation relative n translation of B relative to A. So in this case, it involves both n rotation and n translation, and here it involves only n translation. So the equations that we will use, if I can go back it, okay, if I can go back to this, so this will be the equations involved if there is no n rotations. If theta A, theta B 0, so this term will be 0, and we have only this term which will cause moment, n moment, okay? N moment. If there are n rotation and relative n translation, then both rotations, n rotations and n translation will cause n moment. So these are the set of equations that we are going to use. Now, to solve these equations, I'm going to go to another screen, which is a kind of whiteboard that I have already write down the solution process, and let me switch to that. And please tell me if whether you can see the screen, okay? Now, class, can you all see the screen? Okay. Yes, are you all able to see the screen that I share? Okay, okay, thank you. Okay, so here I have already written down the solution process. Okay. Now here, this is example 2A, where we have n rotation 0, n rotation both 0, but there is n translations. So the first thing that we will do is we will then write down the corresponding n moment. Now the n moment here that I'm using, n moment here that I'm using here is instead of MA and MB, we can also write MAB or MBA. So this is to indicate which member. This will give us a clearer picture which member we are talking about, and especially which n. So the first letter gives us which n that we are talking about of that member AB. And here also this one MAB means we are talking about n moment of this member AB at NA. And here MBA means we are talking about n moment of NB of member AB. Okay. So this will give us a additional information about which member we are looking at. This will be useful when we have more than one members. Okay, sometimes we have more than one members, A, B, B, C. So this would be a useful symbol that we use. So now this, if you recall, relate to the slope deflection equation method. Okay, we are going to have n rotation 0. So the only terms that will be will remains is only this term here. So because n rotation 0, if you refer back to the original slope deflection equations and putting the n rotation 0, theta A, theta B 0, so we end up with these equations for MAB, which is moment at NA, and the same thing for moment at B. So the same thing, so we have the same equations here because this relative n translation will cause the same moment at NB and NA. Now, for the case where you have relative n translations, we need to write down the equilibrium equations considering the whole column and the whole members here, which is we look at these whole members where there is an n relative n translation delta, and there is an axial force P acting here, of course. It's axial P acting here. Then we write down for this column, which is relative n translation delta B relative to A. Okay? And with the n moment here acting like this, so we have n moment MAB, n moment MBA, and we take moment at A here, take moment at A to be 0, so this is the equation that we get. You take moment equilibrium, okay? Moment equilibrium equation at A here, so this is NA here. This is NB. So we take moment equilibrium at NA. So P delta will be equal to, or P delta minus MBA minus MAB. So this is just moment equilibrium equations. So that will be equal to 0. Okay. Then we substitute MAB, MBA from this and this equation into here. So what we get is this equation first. Then we need to rewrite these equations in such a way that we can first factor out the EI over L. We first factor out the EI over L by dividing this with EI over L, so that we can factor this with EI over L. So here EI over L, we want to factor it out first. So then after that, this EI over L, we can then just work with this equation here. So this is the first thing, we transform this equation, or we rewrite this equation. This is the rewriting this equation by taking out, factor out the EI over L. Then we want to rewrite this. We rewrite this in such a way that it will become like this, because we want to factor out. We want to make it has a common terms like delta over L as well. So what we do here is, this is just coming from here, just PL, just take it up there. So this is coming from these terms here. Then remember K square. Okay, remember our K square class. K square is P over EI. K square is P over EI. Okay. So we take note of this. K square is P over EI. So P over EI is substituted as K square from here. P over EI substituted as K square. Then we want to make this delta over L appear here. So we divide this with L, and you divide this with L, then you have to multiply also with L. So the result is we have from these terms, take into consideration K square is P over EI, then we want to make this term appear. So finally it becomes like this. So next, we can then rewrite this one and this one, we take it out. This one and this one, we factor it out. And then we have end up with these equations, KL square minus 2 alpha N plus alpha F. The whole thing multiplied with delta L equal to 0. So now we have obtained this equation. So the next thing is, remember our aim. Our aim is to find P critical where it is possible to have this. Okay? It is possible to have this N translation, to have this shape. So here we apply the conditions to obtain non-trivial solutions. Non-trivial solution means we want to find the conditions here that will make delta L not equal to 0 possible. Because one of the solutions here, which is trivial solution, is delta over L equal to 0. If delta over L equal to 0, it doesn't matter what value you have for KL here, we will get this equation satisfied. But our aim is to get P critical. So to get P critical, meaning that we want to find the solutions where delta over L is not possible, delta over L not equal to 0. So in order for delta over L to be possible to be not equal to 0, so this thing must be equal to 0. So this is the non-trivial solutions condition that we use. So making this equal to 0, so this KL, the whole thing square minus 2 alpha N plus alpha F equal to 0. So this solving this KL, okay? Solving this equation here, meaning we solve for KL. So we solve for KL, then remember what is K, then we can get P critical. Okay? Because if you, after you get KL, if you square the thing, K square, L square, then if you have a value here, let's say, then it becomes a value A square. This is a value. For example, KL is equal to L, then K square, L square is equal to A square. And then from here, you can get what is, remember what is K square? K square is P over EI. L square is equal to the solution that you get. For example, we use a symbol A to represent it. So from here, we can get P critical is equal to A square EI over L square. Now, to solve this, remember alpha n and alpha f is quite a complicated function, so we need to make use of the trial and error method. Trial and error methods, okay? So we know the solution for this, we know the solution for this is the P critical, and the P critical is the L effective. L effective for this problem class is the effective length for this. The effective length for this problem is L. So if the effective length is L, effective length for this problem, the effective length is L. So if the effective length is L, then we know that the P critical is pi square EI over L effective square, meaning that L square. So we know the solution is this. But of course, this is so happen that we know the solutions, but normally we don't know the solutions. But I want to show you here that the way to solve this problem is to solve this problem directly is not easy. We have to use trial and error methods. Okay. Now I have show you now. Now this is one of the way I think Excel file that I have created to solve a problem like this, where involving especially slope deflection equations. So this asks for some other cases. So what I'm trying to emphasize to you here, to solve this problem, so you have to assume using Excel a series of value of KL, and then solving this equation means we want to solve for KL because alpha n and alpha f is a function of KL. So then when you assume a series of value for KL, then you can get alpha n and alpha f. Then after that, you try to get the value of this equation, which is the KL square minus 2 alpha n and alpha f for a series of value for KL. Then you check from your calculation using Excel where this calculation changes from positive to negative. Then if it changes from positive negative or negative to positive, you're going to get the solutions lying in between that two values. Let me show you using this Excel. So first, I assume a series of value for KL. Okay, so KL is 0.1, 0.2, 0.3, 0.4. These are in radian. Okay, remember these are in radian. So now we want to get alpha n. You calculate alpha n, and also you calculate alpha f. Okay, alpha n and alpha f after you assume a series of value of KL. So this is a calculation for alpha n and alpha f. And alpha n and alpha f is, of course, if we go back to the original equation, alpha n is pi n over pi n over pi n square minus pi f square. Okay, so we calculate here also pi n and pi f first, and then get the pi n square minus pi f square for us to substitute into here to get the alpha n. So this is just the way we program the Excel in order to get alpha n and then alpha f. So alpha f is pi f over pi n square minus pi f square. So we get this value for a series of, so we assume a series of value for KL. Then in order to solve the equation just now, I have a column here, which is here. Okay, so this one is actually the equations that I want to solve just now. So when you, after that, when you get alpha n and alpha f, so here we have to put in another separate column, not this column, this one is for another column. So you have to put in, for example, this one equal to, what we want here is this one, multiply with this one again, go back to the equation and then multiply 2 alpha n plus. So that is this equations. KL square minus 2 multiplied with alpha n plus alpha f. Then we try to get a series of that value. So when we substitute this value that we calculated and then ask the Excel to help us to calculate, then what we are looking for is we are looking for the KL. When you substitute the KL value, the functions here that we want to solve changes from negative to positive or positive to negative. So this is where the answer, the range in between this value of KL and between this value of KL and this value of KL, we can find the answer. So let's see what is this value here, okay? Because it changes from negative to positive. So this one will be between 3.1 and 3.2. KL is between 3.1 and 3.2. So if you want it to be approximate, so we take this center one, which is 3.15. We can take the approximation, let's say 3.15 as the answer. If we want it to be more accurate, then between 3.1 and 3.2, we further calculate for smaller value of KL, increment of KL, in order to find the more exact solutions. So this is one way of solving the problem, which is making use of what we call the trial and error methods, and from there try to narrow down where is the possible range of the solutions. So from here we find that the solution for KL should be in between 3.1 and 3.2. So we take the average 3.15 as the solutions. So the exact one for here is, because we know the solution. So this is just to confirm the Excel calculation just now also. The exact solution here is this one should be equal to pi, which is about 3.1415 or 3.14. So which is about 3.14. So it is between the KL between 3.1 and 3.2, which we confirm or we shown using the Excel calculation just now. So this is the way of solving this. So of course, this is a bit mathematical now. So use the Excel to help to solve this problem.